So if you missed where I said, so these are the parts we want to work with today. These parts here. You got your board shipped, right? Sorry, I'm a little kid. You got these, what do you call these again? What are these guys?
Flats.
Yeah, these are flats, ones. Anybody remember these guys?
Units.
Units. They're absolute units. I love it. Is that as far out as you go? Jeez. That's kind of crazy. All right, we'll work with that. So, clear this off. By the way, real quick, the only other things that are in here are these little bits. Do you remember? Do you remember on one of the videos they were kind of putting these together? Yeah. Yeah. Okay. So these are these. I actually don't really use these manipulatives, but these are nice pastel colors for the most part. And then these guys, we discovered these are not about talking about shapes. These are talking about fractions. So like the red piece would be half. So that's, of course, we're going to bust these out when we come to fractions, which is everybody's waiting for that. Very patiently, I appreciate that. You're like, come on with the fractions, let's get there. Just calm down, we'll get there. So, one thing I want to do, last time we talked about addition algorithm and subtraction algorithm, and one of the steps to this was using manipulatives, right? So let's try to do a problem. Let's try to do, here we go. Got paper. Do I have a pen? I do have a pen. Oh, crap. Here we go. Yeah. So I want you to set up this problem. 329 minus, what do you got, Jeff? 217. So we'll do that first. We'll start off nice. So try to set up 329 and then figure out, using the manipulatives, how to subtract 217. Let me know if you're missing any pieces. Are you missing all the flats? Oh shit, I'm sorry. Yeah, last semester people took these home, so somebody must have liked the flats.
These are cool coasters, man.
What's that?
They're like, these are cool coasters, man.
I like that.
Yay.
They're really tight. They're really tight.
Oh yeah, well, sorry guys. Work with the room that you got. Not the room that you got. I'm waiting for somebody to like get on the floor. You know, if you can spread it out on the floor. Okay, you got it figured out? All right, I like it. I mean, the main thing with this, obviously I'm not going to go around and like watch each one of you do this. But, I mean, it's one thing for me to talk about the manipulatives. It's another thing for you to actually touch them and see them work. And then you always keep in mind that all of this is going to be brand new if you're lucky enough to get an assignment where you're teaching students this for the first time, right? All of this is going to be brand new. And they're going to be fascinated by the bits and pieces, right? Depending on how young they are, you might want to walk around and make sure nobody's, trying to see what these taste like. So what do we got? 329. How do I represent 329? Say it.
3 flats.
3 flats.
2 logs.
2 logs. And then 9 of these things. 9 units. Let's see. That's a lot, John. 2, 4, 6, 8, 9. I feel like I'm being videoed with that dude who's going to come around the corner. Tell me your thought process. All right, so I got my 329. Now, this is a very simple problem, I understand it, but we're gonna build up. We're gonna talk about multiplication and division. Well, we should. That should get a little more interesting. Division especially is gonna be really interesting, but multiplication also, okay, we'll see how it goes. So, how do I then take away, what was it, 217?
217.
This one's pretty straightforward, correct?
Yeah.
So I take away, what do I take away?
2 flats,
Take away 2 flats,
1 long,
1 long,
and 7.
7 of these dudes, 1, 2, 3, 4, 5, 6, 7. I like it. So then what's our answer?
1 flat, 1 long, 2 even.
I like it. So we get 1, 1, 2. 112. What do we think about that? Crazy. Okay. So very simple. I know. Just to kind of, I can't remember if I actually let you guys play with these things before, but that's where we're going to start. Addition is pretty straightforward. But let's do this. Let's do another subtraction problem, but a little more interesting this time. Let's do 211 minus 184. So you know why this is going to be more interesting.
We'll have to transform a flat to 10 long.
So definitely start with 211 and then figure out what to do from there. Now the way we do this, do you have to represent 184? You have to lay that out? You have to lay out 184? No. You put the 211. The big problem is manipulative wise, it's the shapes that you're taking away. So we did this problem last time, but it's been a while. See if you guys remember. 211 is nice. 2. 11. Yay. Now I want to take away 184. Where did somebody start with that? I mean, at the very beginning it seems pretty straightforward, right? You could just kind of do something right away. What can you do?
So you transform the flat into 10 longs?
Yeah, so you can kind of think ahead and realize you're going to have to do something to help out because you don't have enough flats. But let's do this. What would a student do who just did the problem that we just did just a second ago? Couldn't I start this off not even realizing there's an issue?
Yeah.
211 minus 184. So I take 2 flats and I'm going to take one of them. Yes? Because then doesn't this say 2 flats take away 1 flat, right? Okay.
Yeah.
But you can still do what you said, but coming off of what we just did, this might be the first thing a student does. And there's nothing wrong with this. All right, so there we go. So I've done that part. Now I want to take 8 longs away from 1 long. And most students will immediately see that's an issue. Right? And of course, that's where we say we just do what? Yeah, we just take that flat and we, like you said, break it into how many longs? 10, because that's the definition of it. I love it. Right. And again, this is that idea, this, like we said last time, and this is when I was just drawing the pictures on the board because I was being, pre-spring break lazy. I was just drawing these on the board instead of breaking them out. That becomes borrowing. But this solidifies it in the brain, the physical idea behind borrowing. They can physically see what it is. We're taking this and we're putting all 10 of these into this place. Okay. So I'm going to take this. Do I have enough? Did I give you enough flats for this? The longs?
No.
God, I suck. I don't even have enough longs.
There's enough units to make a long.
Oh, that's true. Alright. So let me see. 1, 2, 3, 4, 5, 6, 7. Well, damn it. Anyway, alright, let's do this. There's 10 longs, yes? There's 11 longs. Yes, minus 8. So how many longs am I going to have left?
3.
I have 3 longs left. Okay. Now I still have to subtract 4. So again, now they kind of get the idea. It doesn't matter what shape it is, where I am, and the problem, I take what it is and I break it into its parts. And I don't know, did I give you enough of these? I think I gave you enough of these, right?
Yeah.
Okay. Or you could just do this. I mean, obviously, you could break them down into all their tens, right? But this is like 10, 11 units minus 4 units, 7 units. All right. Of course, the answer is 27. Yes. Cool. And this is the kind of thing that I really hope they don't try to make software to take the place of. The whole part of this is this kinesthetic touching the stuff, right? Especially the cube. The cube is really cool.
Yeah. Very sharp.
Okay. And it doesn't like open. Oh, that's not the Hellraiser. Right?
Yeah.
Probably, yeah, it's really good. It's not. Okay. Now, let's talk about multiplication. I don't know if you guys remember how multiplication worked with manipulatives. So let's try, because we don't have a lot of shapes and we don't have a lot of room, let's try a smaller problem for multiplication. Let's try to do, let's do 21 times 13. So here's how this works. Go back for me. What was when we first talked about multiplication, what was the visual way to do multiplication? Yeah, you would have a rectangle. How long would this side be for this problem? 21, and this would be 13 across, right? So the funny thing is, with the manipulatives, we basically do exactly that. We do, what's 21? 21 would be 2 longs. Let me just do that. Everybody's got 21 times 13. 21. I'm going to put that vertically. Okay. Let's see, am I going to have room for this? I think so. 21. Put that vertically. 21. Now, across the top, I'm going to put 13. Shit. Let's see what I can do. I have to tighten everything up. Is it in there? No. Dadgummit.
Yep.
Not quite. All right. Everything's too long. Okay. All right. I'm there. Yay. Okay. So here's what happens. I really want this to make all the sense in the world. 10 times 10.
100.
100. So you just fit a flat in there. This is where things get interesting. 10 times 10. Another 100, right? Right? 1 times 10. Is everybody?
Yep.
So it's exactly like we do. We're just filling in the array that we would set up. We're just putting it in there. This is 10 by 10. So there, 10 by 10. Bam. This is 10 by 10. Bam. And this is 1 by 10. Yes? So we're just going to put a long right there. So 1 times 10 is 10. And then what am I going to do under each of these? Oh, shit. You can almost see them. under each of these is gonna be exactly what I did down here, that you can still almost see if you sat up in your chair. Alright, sorry. I'm working as well as I can. So 10 times 1, 10 times 1, 10 times 1. Oh, this is where we might run out of longs, huh?
No.
No, I do. I'm gonna steal these two because I don't need them over there. There we go. So 10 times 1, bam. 10 times 1, bam. 10 times 1, bam. And then down here, 10 times 1, bam. And now, what's the only thing I have left to do?
3 units.
Yeah. 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. Okay. Holy shit.
Made it.
Alright, so now I'm going to take away the outer stuff, and now I can count what the answer is. 200. 1, 2, 3, 4, 5, 6, 7. 273. Is that what the answer is?
That is it.
Thank God. Alright. So we get 273. Did I do that too quickly? Is that, you guys kind of get that? You get it? Okay. The timing of when I looked at you was off, so I wasn't sure what
You
it is.
asked the yes and no question.
I understand. That's fantastic. You take that and use it in your teaching. Make yourself as confused as you can be. Okay. So multiplication, again, if you just had enough space and enough pieces, you could do whatever big number you want to, right? We don't have enough pieces or enough space, so we can't really do that. But the idea kind of continues. And again, your students are going to just love laying the shit out, and they're going to love counting because they just not that crazy long ago would have learned how to count. So they're all about just showing off the counting. They're going to have fun with this. Us, we would get very bored putting that shit down again pretty quickly, right? And you're all like, yes, we're there. So, what about division? What about division? Yeah. Let me make sure I didn't forget anything I wanted to talk about. Yeah, okay. So, let's try a division problem. Let me see if I can make one that's going to be semi-decent to work with. Let's do 229 divided by divided by 4 is fine. I want to do that. We got enough flats. Let's do let me change it a little bit. Make it 429 divided by 4. So 429 divided by 4. So go ahead and represent 429 real quick. There we go. That's a bad guy. Okay. So, when you divide something by 4, we had a couple of ways to think about division, right? Measurement and sharing and all that kind of stuff. But basically, what you're doing is, if you had 4 groups, let's look at it that way, and you had 4 flats, you have 4 groups, how much does each group get? Yeah, so then you can kind of work the students. You've already kind of talked to them about measurement and sharing and that idea. You can kind of get them to a point where you're saying to them, visually, manipulative-wise, what you're looking for is a group of 4 of the same shape. You would take one of them. That would be the answer. That's what each thing would get. Does that make sense? I mean, I know you know what division is, but just in terms of manipulatives, okay. So when I divide the flats by 4, 1. Now what's the problem when I get to this point?
Break them up.
Yeah, I've only got 2 longs. I can't cut those in 4s, right? Oh, and then, of course, yeah, this is where we have So, if I were to, all right, let's see if we can do this. I start looking for groups of 4, so there's 4 there. See, what's the best way to do this since I don't have enough? How many units do we have? How many units do you guys have? Can you break up one of your longs into 10 units?
Yeah.
I think so, yeah.
Actually, 2.
Okay. I almost can do, I'm like 1 unit short of doing both.
Here you go. Here you
I don't know if everybody can do it though.
I can
go.
Did everybody break both their lungs up? Do you have enough units? Wow, cool. So I was only mean to myself, okay. Let's see if I counted right. 3, 4, 5, 6, 7, 8, 9, 10. Wow! Okay. So the student will, you want to reinforce this to them that this still represents the same number, right? So then all they have to do, what are they going to start, what are you going to have them do with their little clustering of units?
Divided by 4.
Yeah, so find a group of 4, right? Okay, so here's what you can do physically. Find a group of 4, take 1. Oh shit. It's going to happen somewhere. Is everybody with me? Let me do that again. Find a group of 4. That divided by 4 would be 1, bam. Another group of 4. 1, bam. Another group of 4. 1, bam. Another group of 4. 1, bam. Oh shit. Another group of 4. 1, bam. Another group of 4. 1, bam. Another group of 4. 1, bam. And then you get this dude, right? Alright, let me stop for a minute. I forgot what the problem was, so I'm trying to do this all manipulative, so I don't want to think ahead of time what the answer's supposed to be. So I don't even know if I've done this right yet. Alright, we'll find out. Is everybody with me? Do you guys get the same thing? So when you do groups of 4, of course, just like this was 1 for the group of 4, that's 1 for that group of 4. And what is this going to represent?
4.
Yeah, I like it, but they're not going to know that yet.
Oh.
Yeah, but go ahead. Remainder, okay, which will eventually become a fraction. Yeah. So what's the answer then? What's this?
107.
107. Remainder
125.
1. Yeah. So this is 107. Does anyone see if that's the right answer? 107 times 4 would be 428, right? And the remainder 1 makes it 429. Kick ass. So we did it. We did it. Now, what I wish I would have done, okay. Oh, I got a better problem. Okay, hold on. I really want, okay, this is fun. We'll be good. Will this work with what we got? I think so. Let's find out, Jeff. All right, let's do one more problem, and I want to show you how it relates to our standard division algorithm. Because we all know how to long divide, yes? Maybe some of us haven't done it in a while, but if you really had to, you could set it up and blah, blah, blah. Okay. So let's do this. Let's do one more of these, because we are gluttons for punishment. Because if you're a glutton for punishment, it makes this class easier. So let's do 575 divided by 4. I like it. 575 divided by 4. I think I'm gonna run. see everything I'm doing. Now I'm going to step through this a little bit with you, because I have certain points I want to try to make. Alright, so go ahead and set up 575. So I'm going to set up 575. I'm going to do this. I'm going to do, see this already? This is too bright. 500. I'm going to do that. I'm going to do like, those are the flats. These are my longs. Did I count that right? Yes. And then I got my units. I'll do like little, I only need 5 of those stuff. If I could just count, this class would be so much easier for me. Okay. Everybody with me? So there's 575. When you start to divide, I want to make a point. What's the very first step? The very first step is pretty easy. What's the very first step? Or is it easy? I don't know. Maybe it's not. I don't know. Very first step in dividing this by 4. So start with these guys. Do you see a group of 4? Yes. So if you see a group of 4, you can group them, and then you can represent them by 1. Okay. What's going to happen with the dude that's left over, the flat that's left over?
He's going to
You're
going to break it down?
going to break it down. 11. And again, if you don't have to follow along with your list, I don't even know if you have enough pieces for this, but watch. If I break this down, I'm going to break this one down into 10 ones. Okay? So now what do I do? Same thing we just did. Same thing we do every night. So there's a group of 4. Bam! We got that one. Here's a group of 4. Bam! There's a group of 4. Bam! And then here's a group of 4. Bam! And then now there's one left. Right? So what I'm going to do now?
Bring it down.
Right now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's a group of 4. Okay. Bam. Here's a group of 4. You guys, isn't this exciting? You guys alright? I appreciate you're all keeping yourself well behaved for this exciting. And then of course what's that represent? Now, immediately, so what's the answer here real quick?
143.
Now watch this. How do I do this long division? Can you guys just take a minute and do the long division? I'll catch up to you. Long divide 4 to 575. Exactly what you wanted to do. Last week you're sitting around, spring break. I want somebody to make me long divide shit, man. Somebody, how does this work? What are you guys doing out there? What's the very first thing you guys wrote down?
A 1.
A 1. 4 goes into 5 once. And then you, right? Isn't that exactly what we did here? Didn't we subtract these 4? Yes? Oh, you guys, you're all like, yes, Jay. Exactly what this shit we did. I was here when that happened. All right. So there's 1 flat left. But then don't we add it to the 7 to make 17 frickin' longs? Yes? There's the 17 longs. All right. You might have been taught it this way, but you can't remember. Can you guys remember exactly when you learned long division for the very first time?
3rd grade?
But do you, not just when, but can you remember it actually happened?
Yes.
You can remember it happened. Were you taught? I don't know how you were taught. Or did they just show you the thing and say, do it this way? I don't know. This is the appropriate way to do it. You connect it with the physical toys they got to play with. You connect it and you say, all right, if you don't have the toys to play with, we're a little sad. but we still gotta do this division, you know, just because, right? But then you say, didn't we get 17 longs? We didn't. That's 17 longs. 4 goes into 17. We're going to do the full standard, just to full up. There's a few things you're going to have to like step through in a minute, but let's just do it like we totally know it. But that'll be 4, right? 1, 2, 3, 4 groups we got, yes?
Yes.
4 times 4 is 16. There was the leftover long, and we converted into 15 units, right? 4 goes into 15 3 times. 1, 2, 3. 3 groups of 4. 12, 3 remaining 3. Okay. Not like, this isn't like, you know, this isn't like amazing shit, but it's probably something you never thought of, that there's a physical interpretation of what this is doing. And there's the physical interpretation. Using parts based on our number system, the place values of our number system. It's crazy. Okay, I'll let you. Maybe. Okay, again, I know. I'm a math teacher. I understand that most of what I talk about is not the most amazing stuff in the world, but this, it's a little bit interesting.
I actually don't think I'd ever used the long division or seen it made.
Oh, yeah? Okay.
Even in school, you know, I'd be like, mental math and.
Oh, yeah.
Just looking at calculators.
Gotcha. I stole my. Maybe I did. Oh, I did. That's right. I did. All right. So enough of that overhead stuff. You guys can go ahead and pack your box back up if you want to, and put it to the side if it's bothering you, or you can throw it around. They're built to withstand little kids, so they can take you. So obviously, we'll be breaking out the other components of that. And then there's even more stuff back there that's not in these boxes that we'll get to play with later. Sure. Oh, let me see. Let me get that over there. Quiz, test, practice test. Okay. Okay, that's enough, Jeff. I think it's fine. All right. So coming back real quick to the multiplication part of things. When you have a problem like times 312. That one's pretty straightforward. So there's a, you could even, another way to do this problem with manipulatives, what do you guys think? What's another way I could do this problem with manipulatives? What's the basic idea behind any multiplication? Repeated addition. So couldn't I represent 312? And then how many times? Represented 3 times. And then you go, 900, 1,000, 30, 2, 4, 6. Yay! Yes? You don't have to say it like that, but so I mean, the way we did it, it's not always as easy. I mean, if it was 31 times 3 and 12, do you want to do 312 31 times?
No.
Then you need to have like a district that has enough money to give you a stupid amount of stuff, and then you have to have like a warehouse so that every kid can get 30 square feet of area to lay out their shit. I mean, it's probably not going to help. So what about if we do it a different way? If I say expand 312, do you guys remember? Do you guys know what that means to expand
Let's go.
312?
Let me break it down.
Break it down, yeah. So to be, and then you can distribute, right? I like it. So then you get, that's right, guys. 6, yeah. 6, crazy, all right, sweet. And again, these are all progressive steps to take to get somebody more and more familiar. You always ground yourself in the physical, and then you start building on properties you've discussed. And then, of course, we got our normal standard vertical approach, but let's do it a little bit differently. The vertical approach. So 3 times 2 is 6. 3 times 10 is 30. 3 times 300 is 900, and then you got 936. Anyway, that's basically what we do. We just don't think of it like that. In fact, we don't do that, do we? I mean, do we do that? What do we do? 3 times 8 is 6, and then right next to it, we would put 3 times 1 is 3. Yes? That's what we do. Okay. I like it. So this is still like an intermediate step before they get the full algorithm that we use. That's the thing that I think it's really easy to forget. The basic way we do anything, addition, multiplication, all that kind of stuff, had to be built to get to. So when people say, why are you teaching them all this weird shit? Why don't you just show them, why are you doing this shit? Because you got to build on what they're familiar with already. You can't just, anyway. So as a teacher, hopefully you agree that there is a purpose to doing these intermediate steps before you just show them, here's how everybody does it. You don't want to do that first day. That would suck. They have nothing to build off of. How can I do something like this here with 34 times 12? Something similar to this, right? But even break it out more.
Would you do it on both sides?
You could. Now here's one thing. You could do this, right? And then you got 34 times 10 plus 34 times 2. And then you got
340.
34 is 30 plus 4. 34 is 30 plus 4. Right. Now I could have, at the very beginning, broken both out, but then you have to talk about foiling, which is something that you got to kind of work towards. But if you do it like this, you kind of make 2 little problems, each of which I can then break up. I'm kind of foiling, but not really. I'm just using distribution twice, which is all foiling is. Okay. Not too bad. It's pretty simple. It's pretty straightforward. And of course, what is all that? That's all right. Yay! Okay. Oh, okay. I'm gonna show you this. Okay, I can't remember if I signed any of this, but it's not too. It's a little. Anyway, do you remember the lattice method?
Yeah.
Okay. There's a lattice method for multiplication. So let's see. Yeah, let's do, did I do that? Yeah, let's do something more interesting. Let's do 89 times 73. So what you do, put 89, you put 73. Okay. I'm not going to spend a ton of time on this. What's 9 times 7? 63. See that? 9 times 3. 27. 8 times 7. 56. And then 8 times 3. 24. So you get 7. 3 plus 2 plus 4 is 9. 6 plus 6 plus 2 is 14. Carry the 1. 1 and 5. 6. Can somebody double check that for me? Seems about right.
Yep.
All right, sweet. Not, yes?
Can you go over that one more time?
Okay. You saw how I got each of these 9 times 7, 63. Right, so this box here is for the 9 and the 7. Does that make sense? You see how the 8 and the 7 are here, and the 8 and the 3 are here. I'm sorry, here, Jeff, good job. So 9 times 7 is 63. 9 times 3 is 27. 8 times 7 is 56. And of course, if I had like 1 times 7, I would put 0, 7, right? Okay. And then 8 times 3 is 24. And then you just add. Now, let's do this. Let's see if we can see why this works doing it this way, right? The standard way. So what are you going to get? 9 times 3 is 7. The 2 goes to the next place, yes? I said 9 times 3 is 7, which I love. You can clip that if you want. It's 27. We're carrying it over. 3 times 8 is 24. Add the 2, right? You get 26. So 7, the 2 went into the next place. It's not really, you can't really see this that well. So 7 times 9, 63. Carry the 6. 56 and 6 is 62. You can sort of see the, you can't really. I'm trying to see if we can, to be honest, I hadn't done this until now. I was curious if you could see the connection, and you really can't see it too well. I mean, there's the 7. There's 6 plus 3, right? 2 plus 2 is 2 plus 12, but the 1 is going to get carried, right? Yeah. And the 1 gets carried and makes 6. So, I mean, it's all in there. The lattice just sort of forces them in the right place so that when you do it this way, they're all sort of like carried over to the next place for you. But it's not a method that a lot of people have ever seen. Has anybody ever seen that method? I think a few of you guys said you had. Anybody ever seen that before this class? No. The lattice method for anything? Yes? Yeah, I knew somebody had. Okay. But it depends on your teacher. I'm thinking the really older teachers probably know that, the lattice method, because they used to actually have paper that was sort of set up for lattice stuff, and then we just don't print it out anymore. Anyway, okay, so I just want to show you this once, but I'm not gonna focus on that at all. Okay. Blah, blah, blah. Okay. So let's talk about division. We already did the manipulative stuff. What's really curious about division is, let's see. Well, I'm going to do a division problem in a way you're really not used to. All right, so let's do this. 5,891 divided by 28. So let's see. Think about 30 into 6,000. How many 30s are there in 6,000?
200.
200. So let's not put 200 in. Let's put 200 here. What's 200 times 28? What's 2 times 28? 56, so it'll be 5,600, right? Now, is this our standard algorithm that I'm doing? Hell no. But let's see what happens. So it's 291. 28 goes into 291 how many times?
10.
Yeah, like 10. Yeah. So 10. So this will be 280. So it'll be 210, remainder 11. Now, the thing about, let's see, does that look right? Did I get that right? I did, yeah, look at me go. Yeah. All right. So the funny thing about what I just did is, you don't, let me see, what's another way I could say this? It doesn't matter, if you do it this way, it doesn't matter if you got that right, right? Because it's going to eventually catch up to itself. Remember, multiplication was repeated addition. Division is repeated subtraction. So as long as I end up subtracting as much as I need to kind of kill this number all the way down to the remainder, and then I add up everything I did, I'm golden. So it don't have to be perfect. Let me try another one, because that one was too, I pretty much did exactly what we're supposed to do. What do you got, Jeff? I don't know, dude. Let's do 32 into 49.94. I like it. So let's say like 100. Let's just say 100. So that's 3,200. So what's that left? 1794. Okay. So what do you guys think? Like 30 into this. What do you guys think? How many? What do you think? Think about like 3 into 17, right?
Like 3, 5.
5, so 50. You guys see what I'm saying? So I'm just trying to get something close that goes into it. I don't have to be perfect this way. 50. 50 times 32 would be 1,500 plus 100, so it's 1,600. Is that cool? Like, right? 30 times 50 is 1,500. 2 times 50 is 100, so that's 1,600. So what I got left to work with? 194. So like 5. Let's do 5. 5. All right, 5 will be 160. Yes? And that's 34. So isn't that 132?
Yeah.
I don't know if you guys are with me.
Yeah.
Guys,
That's 2.
it's a little weird, right? You're not used to this, but I really want this. We're kind of subtracting a bunch in each step. And as long as I subtract enough and then count, add up all the subtractions I did. So when I did this, I subtracted 132s from this. And then I subtracted 50 and so forth. Now I just got to subtract one more, and then I got the remainder. So what do I got? 56, a 156 remainder, 2. Kabam. Is that right? I don't know. Hopefully it's right. That'd be great if it was right.
Yeah.
Be like icing on the cake. Okay. So let's try this problem again, just the normal way. Not this freaky ass shit that Jeff's doing, right?
What's that method called that you're putting in?
This is like an intermediate algorithm, is what the book calls it. Let me see if I can find it. Blah, 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 blah. Is it one of their intermediate algorithms? No. Oh, I'm in the wrong place. Yes. They just call it intermediate algorithm. So page 153.
Okay.
Yeah. But now, I mean, what do you guys think when you see this problem? What do you guys, how do you figure out, well, this is 32 into 49, right?
Mm-hmm.
That's obviously one. Let's see. Yes. Now watch. How does that relate to what we did here? Isn't that 100? Doesn't that 1 there, the place it's in, it represents 100? And then this other shit was just me collecting the other bits. So again, intermediate algorithms are things you use to kind of move students towards this, and you're always making connections to what you did before. I don't know if you guys remember, I know we're not done with this, but remember when we had like 82 divided by 7, so we did 82 minus 7, right? I think I pretty much, and then minus 7, do you remember that? And then you just counted how many subtract. That's exactly what this is. This is being a little more precise and a little more focused. And then, of course, you bring down the 9. 32, 179, which is basically sort of like where we were here, right?
Yeah.
Okay. 32 and a 179 looks to go maybe 5 times, right? That'll be 160 like we got earlier. 194. Just like where we were there. Look at that. Neat. And then this was 6. That'll be 192. And there's my remainder 2. Yay. Okay, I like it. I like it. Nifty. And maybe. But I mean, when you do this way, you are subtracting, but you completely lose sight
that it's repeated subtraction. It's built off of that. You don't think that when you're doing this. This is one step away from repeated subtraction. I subtracted 100 of them. I subtracted 50 of them. So it connects this to this to this, right?
Yeah.
And of course, that's the most efficient way. But to be really honest, this way is sometimes faster than that way, depending on what the numbers are, right? Okay. You guys are all very excited. I can feel it. So last thing for today. Maybe we'll get out a little early. Which is what everybody's really excited about. I get to show off. Let me see if I can remember how to pronounce a certain person's name. I'm going to try. Let's see. But before I pronounce this person's name, we're going to talk. We're getting into. We're done with chapter 4. We just finished chapter 4. Just want to make sure that. Yay! Celebration. Okay. So chapter 5, section 5.1. This is the one that we've already done some work in. And it starts with prime numbers and composite numbers. Can somebody tell me prime and composite? What the hell's that all about? What's a composite number? Does anyone remember? Versus a prime. They're basically opposites.
That's more than two factors.
I like it. When in doubt, read from the book.
Yep.
So composite, it kind of makes sense. It's composed of more stuff, right? So like 8 is 2 times 4. It's more than just 1 times 8. Whereas a prime number, of course, the only way to break it down is 1 times itself. Okay, I like it. So watch this. It's kind of neat. Well, first off, this is going to be remarkably neat. You ready? I mean, watch Jeff. Watch Jeff just write numbers. Oh my God, I can watch this all day. This is, oh my God, this is amazing. Jeff, this is, I had no idea. You just have a Netflix special where you just do this and you make so much money. All right, that's enough shit. Now watch. Now, why does this work? If I want to try to find the prime numbers, one we don't consider. He's a unit, he's like that. If I circle 2 and then I cross off everything, all the multiples of 2, I start counting by 2 and I cross them off. 2, 4, 6, 8, 10. Why is that? Why is everything I'm crossing through composite?
Because you can divide them by more than.
Because those are the ones obviously going to divide it by 2, because they're all multiples of 2, right? Now do the same thing. Now here's 3. If I count by 3, I already killed 6. 9's dead now. 12's dead already. 15's dead now. 21's dead now. 24 was already dead. 27's dead now. Right? If I did that forever, and then you go to that, and then you cross off that is 5. And then you go to 7. And then you cross off to 7. All right. So this is called the sieve of, oh, you were going to spell it too, Jeff. All right, let me see if I remember how to pronounce this person. Here we go. I remember. Eratosthenes.
Almost.
No, that's it. Eratosthenes. Eratosthenes. The th is a th, not a t from the final.
So the sieve is like for like
Does that mean?
like for like a sand, like sifting.
Yeah, like I said for yeah, they're like I think about people going for gold.
Yeah.
And you sift. When you sift something, you're using a sieve. Anyway, that's what this method is called. That's one method to try to find the primes. Are you guys all aware that there is a huge undertaking to find that not only the next largest prime, so like every week or so, I'll check to see if they've discovered the next largest prime. So they're in the realm of numbers that have about, let's see, the last time I checked, was it like in the 57 places, right?
Wow.
Do you know what I mean? Like 1 followed by 57 zeros. Are you with me? So they're up in those kind of numbers. So they're always trying to find the next. And the really big thing, if you could, oh kids, get ready. Oh, do you want to be like a big name in the math world, meaning maybe 1% of the whole world would know you. No? Okay, I understand. I love that somebody's on me like, nope, don't want none of that shit. All right, I understand. If you could find, so here's what you want to avoid. Don't accidentally find a pattern to the prime numbers. We have no idea if there is a pattern to the prime numbers. So did your teacher for a while, and is he still trying every now and again to find a pattern? Yes, he is. I'm trying. I'm like, there's got to be a pattern somewhere. But do you guys kind of follow what I'm saying? So if there was a pattern, that would be stupid big. Now you might go, how does that help solve the gas price problem? Well, I don't care. Shit, nobody can. But I mean, it's just huge. If we could predict, if we could actually just have an equation to tell us what the next prime number is, that would actually kick into a few different areas in mathematics. And then you never know which one of those might actually do something practical, which is always, just icing on the cake for us mathematicians. If it doesn't, it does something practical? Holy shit. Okay, I'll stop. One more idea before we get to the thing we've done before. Okay. There's an idea of divides, and it comes along with notation. So, I mean, does 4 divide 8? What would you say? I don't know if you ever heard it sound like that, but what you got? Does 4 divide 8? Does 4 divide 8? Yeah. Yes, it does. It divides 8. Why does it? So what does divides something mean? It means it goes into it with no remainder, right? So if I write A line B, this is red, A divides B, and it means there exists a whole number, we'll call it X, such that AX equals B. It's crazy. So 4 divides 8 because 2 exists. It's a number that exists. 4 times 2 is 8. Bam. Incredible. So the main thing there is just the notation. I don't know if you guys have ever seen that notation before. So it's not A divided by B. It's not B divided by A. It's A divides B. It's a statement about what something does. It's not a problem to solve. I'm not your problem to solve. All right, okay, yeah. So, is this true? No, so then you do this, yeah, all right. It's kind of silly. It's a little bit silly. I always thought that was a little silly. But, at the same time, it makes sense. It don't do it, so we just put a little line through it. Or don't divide 17, so hey. Okay. So that's just a little side note. I mean, that's just notation. So the thing that I have touched on before is related to how to tell if something is divisible by 3. Let's see if you guys remember. So let's go through them one at a time. How do you tell if a number is divisible by 1? It exists. How do you tell if a number is divisible by 2?
It's even.
It's even. Yeah, it's great. How about 3? Does anyone remember about 3? That's the one I'm pretty sure we talked about.
Doesn't the last number add to 3? Or
No.
Not the last number. You might be thinking about 4.
Add the 3.
All the numbers, all the digits, add to a multiple of 3. I'll do an example. So for example, oh shit. Oh, okay, that worked. Okay. So, what do those digits add up to be? 24. Is that divisible by 3? Yeah, so this 3 divides this because 3 divides that. Or to put it less confusingly, you add these damn things, they add 24. 3 goes into that, so therefore 3 goes into that. Isn't that crazy? Somebody do that for, what is that? Anybody do it?
38,099.
Beautiful, no remainder, right? I love it. Some freaky shit. 4. I'm almost certain we talked about 4.
The 25% thing there.
Something like that. So for a number to be divisible by 4, the last 2 digits have to be a number divisible by 4.
Because then everything is hundreds.
Exactly. So for example, 1087923111144. Why is that divisible by 4?
That's 44. So it's
Because the
11.
last 2 digits make 44. That's divisible by 4. So the whole thing is divisible by 4. The reason that works is because 4 times 25 is 100. Therefore, 4 goes into 200, 300. It goes into any 100 plus 4 plus 8 plus 12. So as long as the last 2 are good, first chunk is some multiple of 100. So then it goes into everything. I don't know if that makes sense, but that's the rule. Now 5, you got it. If you don't know 5, I'm just going to cry for a minute. Ends in 0, 4. Okay. What about 6? What about 6? Is 6 prime?
No.
What is it made of?
3 and 2.
3 and 2. So, in order to be divisible, let me tell you. Oh my God. I just brought spring break with me in a bottle. In order for it to be divisible by 6, there it is. It has to be divisible by 2 and 3. Think about that. Doesn't that make sense? If I can divide by 2, I can't say divide. That's hard for my job. If I can divide by 2 and by 3, then obviously I can divide by frickin' 6. Yes? So what does that mean practically? It's got to be even, and all the digits have to add to a multiple of 3. So would that be divisible by 6?
Yes.
Is it even?
No. Oh, no.
So no. So it's divisible by 3, but it's not divisible by 6 because it's not frickin' even. Yes? So any number, 1, 4, 3, 2, what is that? 5, 9, 10, 11, 13, 14, 15. There we go. All right, so that number is divisible by 3 because I forced it to add to be 15 if I added correctly. And it's even. So it should be divisible by 6. Can somebody check that? No, okay. 1, 8, 6. I lost that.
1,868,572.
Okay. So 6 has to be even, and all the digits add up to a multiple of 3. Oh.
Yes.
8. All right, 7 is weird. I'm just gonna put weird. I'm probably gonna misspell weird. Is it I before E and weird? 7 after C or W? Is weird just weird? I can't remember. 8. Now here's something funky. For the last 2 digits had to be divisible by 4. 8, the last 3 digits have to be divisible, and the reason that is 4 goes into 100. Yes. 4 divides 100. 8 does not divide 100, right? But 8 divides 1,000. Therefore, as long as the last 3 digits are divisible by 8, it doesn't matter what's before it. So that rule kind of sucks. Because I can't just look at a 3-digit number and tell if it's divisible by 8 automatically, right? Okay, so the last 3 digits make a number that's divisible by 8. Okay, good job, Jeff. Now 9 should have a rule related to what? Yeah, 3 is, but that's 6 because 9 is not even. So 9 should definitely be related to 3, and it totally is. It's exactly the same rule, except all the digits have to add to a multiple of 9. Is that cool? So if you have a number and it adds up to 6, if all the digits add to 6, is it divisible by 3? Yes. Is it divisible by 9? No. What's it take to be divisible by 9? They have to add up to be a multiple of 9. So the number 1, 1, 2, 2. Here you go, Jeff. Is that divisible by 3?
Yeah.
Yes, because they add up to 6. 3 goes into 6. Is it divisible by 9? No, because they add up to 6 and 9 does not go into 6. You guys see the difference?
Yes.
Okay, I like it. Is that divisible by 6? It's even? And the numbers add to a multiple of 3? Yes, it's divisible by 6. Good guess. Okay. And what's it take? Now here's the biggest one. What's it take to be divisible by 10? Sorry. That's pretty good. We did pretty good. I don't know if you guys are 100% with me on some of this weird shit. There is a divisibility test in the book for 11, which is interesting. I'm going to let you read through that. I don't think the book talks about 7. There is a rule for 7, and it gets really, really trippy. But yeah, I couldn't remember if they talked about 7, but no, they don't. There is a rule for 7, but it's kind of involved. I'll see if I ever feel like showing it to you, because I can't even really remember it right now, to be honest. I just remember it's involved. Yeah, I think that's enough for today. What do you guys think? It's a little early, but we're good with that, right? Okay. So if you have any questions, you can hang out and ask away. Don't forget the quiz first thing on Thursday. We'll finish up chapter 5 Thursday, and I'll have the practice test for you guys. Yeah, if you could just, here's even better. If you guys could, you're good, come on. Could really help me out. Take your boxes and into this crazy bathroom here.
Appreciate it. You must stick around, yeah. No. Gonna take advantage of the AC. Hey, not much, man. Good. Then get this done as much as possible. How about you?
Thank you.
Is there other questions?
Yeah.